So in this video, I will be presenting my Python algorithm for computing the multinomial theorem. So as you may recall, here is the multinomial theorem. And it involves taking sums of terms such that k1 plus k2 all the way to plus kr is equal to n. But how do we find the set of k's that equal to n? Well, in this presentation, I will show you exactly how, in a systematic way. So we begin by asking, how many distinct non-negative integer valued vectors, x1 all the way to xr, satisfy the following equation of x1 plus x2 plus all the way to plus xr is equal to n. So we can actually make a visualization of this, and we'll use that to find these values of x's. So here we have an example of 1, 2, 3, 4, 5 balls and 2 blue dividers. So what we're going to do is that we're going to have slots for each of these 5 balls and 2 blue dividers. There should be 1, 2, 3, 4, 5, 6, 7, yep, 7 slots, which is 5 plus 2. And we're going to arrange them in the slots such that the balls are divided into 3 sections, and the number of balls must be equal to 5. So here is one possible way we can do this. Here is another possible way we can do this. We can have 0 balls on one side of the divider, 3 balls on the other side of the first divider, and 2 balls in the last section. Or we can have 0 on one side, 0 on the other, and 5 on the other side of the dividers. So, in general, we need r minus 1 of these blue dividers and n of these balls to fill in the n plus r minus 1 purple slots, thus dividing the balls into r sections. And there are n plus r minus 1, choose r minus 1 ways we can arrange the balls and dividers into these purple slots, of which there are n plus r minus 1 of these purple slots. Alright, so now that we have a visualization of what's going on here, let's move on to my Python program, which uses the numbers 0 and 1 as balls and dividers, respectively, in each possible list of balls and dividers. You'll see. Alright, so in order to explain my program, I used a Jupyter notebook, and it will be about the polynomial expansion using the multinomial theorem. So in the first part of this, we are going to generate all vectors whose components, x1 all the way to xr, are non-negative solutions of x1 plus x2 plus all the way to plus xr is equal to n. And so in this case, we have initialized the variable n to 3 and r also to 3. So what we're doing is that we're saying like something like x1 plus x2 plus x3 raised to the 3rd power. Alright, so I've created a function called nested loops, and what it does is that it uses the for loop and recursion combination to nest the loop up to any kind of level, so num of levels. So the number of levels that we want to do here is actually going to be n plus r minus 1. This is because we want to generate a list of length n plus r minus 1, and this list will end up containing zeros and ones of all possible combinations. This is because in the for loop, we range I from 0 to 1 inclusive. So it's going to be 0 and 1. And because of this recursion, we're actually going to get all possible possibilities of all possible arrangements of zeros and ones in these n plus r minus 1 slots. And you'll see what I mean on the next slide. All right, so now let's use our function to generate all possible sequences of zeros and ones. And you'll see here that we have all possible sequences of zeros and ones in lists of length n plus r minus 1, which in this case would be 3 plus 3 minus 1, which will be equal to 5. So 1, 2, 3, 4, 5. And as you can see here, we have differing values of ones, like different numbers. Like, how many ones do we have in each list? We have, well, different numbers of ones. And that can range from 0 ones to 5 ones. So we want to take these such that we only have 2 ones, because we want to divide the zeros into 1, 2, 3 sections, because r is equal to 3. So what we're going to do here is that we're going to use a list comprehension to filter this list of lists such that it only contains 2 ones. And here we have done that on the bottom. All right, so now I've created a function here that takes in each of these lists within that one list of 5 total elements, 2 ones in each list, right? It's going to take in one of these lists, and what it's going to do is that it's going to create a new list that is the number of zeros on each side of the dividers. So it's going to create a vector of all possible numbers that add up to n, or 3 in this case. All right, so now we will apply our function to each and every one of these lists within that one bigger list, right? So we're going to do parse filtered results. And we're going to add it to a list of lists called rnums list. That will be a list of all possible numbers that add up to n, or all possible vectors of length 3 that add up to 3. So we have printed the results over here, and you'll see that these are all possible arrangements. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them, which makes sense. All right, so now we're going to make the terms in the summation. And we'll need something that could compute the product of factorials, because the multinomial coefficient consists of n factorial over k1 factorial times k2 factorial all the way to times kr factorial. So we have a function here that will do that. So we also have a make term function that utilizes that function up there that computes the product of factorials. It's going to put that as the first component of the term, and the second component of the term will consist of x1 to the k1 times x2 to the k2 times x2 to the k3, all the way to xr to the kr. That's what it'll do. All right, so now if we use a for loop to iterate over all of these lists of vectors of length 3 that add up to 3, and we compute the terms in all of them separated by a plus sign, then we get our answer right there on the bottom. And if we compare the answer to that of Wolfram alpha on the top and our answer on the bottom, then we'll see that they are identical, which is good. That means that my program works. Alright, so that is the end of this video, and thank you for watching.